lecture, we're going to talk about different column end conditions. In the previous lecture, we derived the Euler buckling equation for pin-ended columns. But in addition to having a column that's pinned on each end, let me just sketch that out. I won't draw the buckling guide. Here we have a pin down here. I'm just going to simplify this with a straight line and a pin on top. We found out that the critical buckling load was pi squared EI divided by the length of the column squared. And again, for our first mode shape. But just like beams, there are different ways we can support columns. We might have a fixed and free type column. Again, it has to have a compressive load applied to it. We might have one end fixed and the other end pinned. And just like beams, we could have both ends fixed. Okay, so we call this one fixed and free, pinned and pinned, fixed and pinned, and fixed and fixed. Now, as you might suspect, some of these end conditions can support more load than others. And I've drawn these in particular order. From left to right, we have an increasing amount of load that these columns can take for a particular length of column, everything else being equal. So a fixed and fixed column can hold the most load for the same length. And then the next one would be your pinned and fixed, a little bit less load, pinned and pinned, even a little bit less, and the weakest one, the one that holds the least weight, would be our fixed and free column. And so in a similar way that we've analyzed the other column configurations, the pin and pin column, we can analyze these column configurations. And we're going to focus on one particular one in this lecture. You can look in the books. You can find the others, fixed and free and fixed, but we're going to look at the fixed and pinned column and get into the details of that one. All right, so in a similar way, we'll have a buckling guide up at the top as we did with pinned and pinned, so that we can maintain the load directly above the lower support. Let me start off on a new page. Right, so there's our pinned and fixed column, and we'll have the length of the column L. I'm going to identify a couple points on here. We'll say that A is down on the bottom and B is up at the top, and we're going to take our x-axis to go up this way this time. On our y-axis, we'll just go over this way. So similar to what we did in the pinned and pinned case, we're going to take a look at the free body diagram of the column in its deformed position. Now, the way this thing is going to deform is a little different than what it did before. Since this is a fixed end, it's not going to move left to right, it's not going to rotate, so it's going to be kind of stiff down here. And the deflection, the deformation, is going to kind of be skewed towards the top end. Okay, so we have maybe some kind of shape like that. Let me draw this free body diagram out here separately. Again, I'm just trying to schematically show this. I'm exaggerating it a little bit here. But we have our fixed end down here at A, which we can have a horizontal force. Call that the y direction, so that's AY. We can have an axial force, AX, and the fixed end can support a moment. I'll call that MA. Up at the top, we have a vertical force P and a horizontal force that goes this way, I'll call it HB for the horizontal force at B. We don't have a moment up at the top because it's a pin condition up at the top. In our coordinate system starting down here, I'm going to take and make a smaller free body section at distance x to figure out what our internal moment is. We're going to apply EIV double prime is equal to M again, like our beam equation. So I'm going to cut this at position x, and I'm going to draw the free body diagram. I'm going to draw the top part of it. Now we talked about how the deformations are somewhat exaggerated here. The distance from where the neutral axis used to be to where it is now at that particular spot is the deflection of the column or the beam. That's little v. We have our forces up at the top. And now we have a shear force. That's a capital V, a bending moment, and an axial force on this cut. And that axial force will be equal to P. I'm going to call this little spot right here O. And we're going to do the summation of moments about O. Let's see. We got HB times the distance, which would be L minus X. And by this convention, that'd be rotating in the positive direction. We've got little p times v, which would be rotating in the opposite direction. And then down at the bottom, we have the moment m, which would be in the minus direction. Equal to 0 for equilibrium. So if we solve for m is going to be equal to hb times this quantity, L minus X, minus PV. Like we did before, we're going to put that into our second order equation for beam deflection and have EIV double prime is equal to M. And I'm just going to write it down again, HB L minus X minus PV. I'm going to put all the V terms on one side. And I'm left with some stuff on the right-hand side. When that happens, what I have is what's called a non-homogeneous ODE. And if you remember, if you've taken a class in differential equations, you might remember the terms a particular and complementary solution. That's the approach that we're going to have to take to solve this. But before we do that, let's do what we did before, and let's divide both sides by EI. So we'll look at a particular and complementary solution. Let's do our alpha squared thing again. Oops, I need a V right here. So we have V double prime plus alpha squared V is equal to HB over EI times L minus X. I'll leave my picture there for a moment. So like I said, we need a particular and complementary solution. Now, one of these, you set the differential equation equal to 0, and the other, you look at the form of the right-hand side, the non-V terms, to help you figure out what the form of the differential equation is. And then you take and you add the particular and complementary solutions together. I always forget which one's which, but in my notes, it says that the complementary solution is when you set the ODE equal to 0, and the particular one is when you look at the right-hand side. Now, when the ODE is set equal to 0, we've already talked about that. The solution to this one is V is equal to A sine alpha x plus b cosine alpha x. So let's focus more today in this lecture on the particular part. If we look at the particular side, it's the right-hand side is equal to HB over EI times L minus HB over EI times X. In a way that kind of looks like a constant minus another plus or minus another constant times X. So let's call it C. We'll just use plus for right now. Plus dx would be a form of the solution V. Let's take the first and second derivative of this V. So V prime would be equal to D, and V double prime would be equal to 0. So if I apply my differential equation up here, V double prime plus alpha squared V is equal to HB over EI times L minus HB over EI times X. If I put in 0 for V double prime plus alpha squared times V, in this case, I can solve for V directly by dividing by alpha squared. All right, and I need a bracket to go around this term. So I'm dividing both sides. Now we know what alpha squared is. If you remember, alpha squared we said was P over EI. So 1 over alpha squared is going to be equal to EI divided by P. So let's see what we've got. HB times P times L. HB times L divided by P. I need to look at the 1 over alpha squared term. Minus HB X over P. And so now we have the particular part. So the total solution is equal to HB L over P, the particular. And we got the HBX over P plus A sine alpha X plus B cosine alpha X. Now, just as we did before, we can apply our boundary conditions. If we look at the beam that I have there, our boundary conditions are going to be at x equal to 0, there's no deflection because of the fixed end. And at x equal to 0, there's no slope because of the fixed end. And at the top of the beam at x equal to L, we have 0 deflection. So let's label these 1, 2, and 3, and let's apply them. If I apply number 1, I will have HB L over P. That goes away to 0, sine goes to 0, plus B cosine of 0 is equal to 0. Okay, so that equals to 1. So what this says is HB over L times P. We move to the other side. So B is equal to minus HB L over P. Let's apply the second one. Now we need a derivative, so we need V prime. Let's write it down here. V prime would be equal to minus HB over P plus alpha A cosine alpha x minus alpha B sine alpha x. So by applying boundary condition 2, we have minus HB over P. The cosine of 0 is 1, so we can have plus alpha A. The sine of 0 is 0, equal to 0. So we can solve this for A. A is going to be equal to HB over P divided by alpha. Now we've got one last boundary condition we can apply, and that's number 3. And that's at x equal to L, V is equal to 0. Let's see, I erased my equation for V. Let me write it in here just so we have it. All right, so now we're going to take and we're going to plug in x is equal to L. Now when we do that, the first two terms will cancel themselves out. And then we have A sine alpha L plus B cosine alpha L equal to 0. Let's work with this equation just a little bit. A sine alpha L plus would be equal to minus B cosine alpha L. Let's take the cosine over here. Sine over cosine is tangent, so we got tangent alpha L would be equal to minus B over A. Let's see what we've got. We know what B is. Now the negative signs will cancel out. We have HB times L over P. And for A, we have HB divided by P in alpha. Now the HB's and the P's will cancel out, and the alpha will flip up to the top. And so we get kind of an interesting looking equation right now. We get tangent alpha L is equal to alpha L. The tangent of some number is exactly equal to some number. Now we've seen something kind of like this earlier in the course, where we said, well, if you got a really small number and you take the tangent of a really small number in radians, you get back that really small number. But that was an approximation. This is very different. This is an exact equality. The tangent of some number is exactly equal to that number. We can figure out what that number is. You can use a root solver on your calculator. You can make a plot. But it turns out the first time this happens, the lowest value is when alpha L is equal to 4.4934. Now there's more digits. It's a transcendental number, but that's 5 significant digits right here. It's close enough. And there are multiple values to this, like I said, but this is the lowest value where that will happen. So you can try this. You can put this in your calculator. Make sure your calculator is in radians, but you put in 4.4934, take the tangent of it, and that'll be 4.4934. Well, let's see what that does for us. Remember, the alpha has inside of it wrapped in there P over EI. Now, alpha squared we defined as P over EI. So let's square both sides of this. Alpha squared L squared is equal to 4.934 quantity squared. Let's solve for alpha squared. 4.4934 squared divided by L squared. Alpha squared is equal to P over EI. I can cross multiply and find my critical load for my fixed and pinned case, which is 4.4934 quantity squared EI over the length of the column squared. So let's label this. That's our critical buckling load for a fixed and pinned column. Remember what we had for a pinned and pinned column was pi squared EI over the length of the column squared for n is equal to 1. Now we said that we expected that the fixed and pinned column would support more load than the pinned and pinned column, and that's true. We had 3.14 squared for the pinned and pinned column. Now we got 4.4934 squared for the fixed and pinned column, so it does support more load. Different end conditions, we can find different values for this squared term right here. Now there's two ways that we can approach this. We can memorize 4 different formulas and those coefficients that go along with it for the length of a column, or we can do something a little different. We can use a reference formula and change the length of the column so that the column will buckle at an equivalent length at the same load. Let me make a sketch. I think this will make a little bit more sense when I show these pictures again. All right, so let's just write our formulas down one more time. We had 4.4934 quantity squared times EI over the length of the column squared. Okay, so all of these have the length of the column L. And over here in the pinned case, we had pi squared EI over the length of the column squared. Again, we're looking at n is equal to 1. So what I'm saying is that for the same length, this holds a higher load. But another way I can look at it is I can say, I can make the column that's pinned and fixed taller, and it will have the same load as a shorter pinned and pinned column. Okay, so what I mean by that is we can come up with something called an effective length. The pinned and fixed column has an effective length that is shorter than a pinned and pinned column. All right, so we're going to use one formula. We're going to use pi squared EI, but instead of using the length of the column, we're going to modify the length of the column so that the coefficient works out, so we don't have to memorize all those different coefficients. We do need to know different K values. Now, if we were to set this equal to 4.4934 quantity squared EI over L squared, we could find this effective length factor. So I have to be a little careful here. We should just say this is the effective length. And those different values are going to be over here, 2.0, 1.0, 0.7, and 0.5. So if I have a pinned and pinned column and a fixed and fixed column, I can have a 10-foot tall pinned and pinned column that would buckle at the same load as a 20-foot tall pinned and pinned, 20-foot tall fixed and fixed column. And then 70%, and then the free and the fixed is 2. All right. So all we need to do now is remember the critical buckling load formula and remember the various K factors. So here this L is the actual length of the column, and this K adjusts the length of the column so that we can use the pi squared instead of all these different values. All right, so in typical homework problems in this section, you will take a look at various end conditions. You plug in the different values for the lengths, and then you need to multiply it by the appropriate K factor based on what it looks like in order to get your critical buckling load.